Hello everybody and welcome again in your channel Thermal Engineering Concept and Principle. In the previous episodes we talked about how to predict the heat transfer coefficient for fluids while they pass through a tube in a laminar and turbulent flow. In the present episode we will go through how can we estimate the heat transfer coefficient of fluids as they pass over the outer surface of the tubes. That is called the external flow. Let us go deeply in our episode, which is presented by Professor Ali Tarat. Welcome, my friends and colleagues, to your channel, Thermal Engineering Concept and Principle. In the previous episodes, we have passed through some methods about how to estimate the heat transfer coefficient in convection mode for fluids passing inside tubes in a laminar and turbulent flow that is called the forced convection heat transfer mode. In the present episode, we will pass through the estimation of convection heat transfer for external flow, where fluid passes over a single tube and we want to calculate the heat transfer coefficient of that fluid, such as air, in applications of air-cooled heat exchangers, including the condensers as well, where they are used in power plants, especially for the gas power plants. Usually they use in their design air-cooled heat exchangers. So for this point, I would like to thank you for your support to our channel, your channel, where we can deliver the useful information to engineers, students who are working in the field of energy. Let us go to pass through the objectives of the present episode. The main objectives of the present episode are a convection heat transfer process, and we will describe this process for an application where flow of fluid over a single tube. The available correlations to predict the heat transfer coefficient of fluid um, while it passes over a single tube. Then we will take a practical case of application where the internal flow exists. And finally, as usual, we will arrive to the closure of the present episode. Convection heat transfer process. One application of such a process is shown in this figure, where airflow passes over a single tube, which could be an industrial heater, as shown in this figure, and then it is heated by transferring energy or heat from the electrical resistance heater to the air, and the flow is perpendicular to the heat exchanger, which is represented by a single tube and the fluid, and it is heated by electrical resistance. Of course, this could be a tube where steam or hot water can be used to heat up air. At the same time, it could be used for cooling when we um, force chilled water to pass through the tube, then heat is exchanged between these fluids. And it is a cross flow because each flow is perpendicular to the direction of the other. This is a simple application where we can find a convection heat transfer process. At the same time, I urge you to go back to the uh, YouTubes and especially the videos which have been published on my channel, and you may find a series of episodes about the application of heat transfer modes and especially the convection mode. So this is how the heat transfer process occurs in a convection mode, an external flow. External flow correlations, there are quite good number of these correlations available in the open literature. Some of them I may mention them in this video. Let us go to one of the earliest um, correlations by Hilbert in 1933, which is represented by Nusselt as a function of Reynolds and Prandtl in the form of equation number 1. And uh, of course, there's a limitation for this correlation, which can be shown in table 1, where we can get the coefficient C and the exponent M from this table, depending on the range of Reynolds number, and it is applied up to 400,000 for Reynolds number, and the properties should be obtained in the film temperature, and it is not applicable for liquid metals as it has been recommended by Hilbert. This is one of the correlations. We have Zokos Kass in 1972. He also has presented a correlation in the same form, but he has added the effect of Prandtl, where a temperature difference is existed, that is at the wall temperature. So the ratio, the Prandtl number, is calculated as the film temperature divided by the Prandtl number calculated at the wall temperature to the power 0.25. And he also prepared a table for obtaining the values of C and M as shown in table number 2. And of course, the properties are calculated at film temperature except Prandtl number at the wall temperature. We have also Churchill and Bernstein uh, correlation in 1977. He presented quite a complicated form of the Nusselt number in terms of Prandtl, uh, Reynolds, um, and as shown in equation 3a, and this is applicable for the range where Reynolds number greater than 100 and less than 10 to power 7, with Nusselt number is greater than 0.2. And he gave us another correlation to be more specific in the range of Reynolds number, as shown in equation 3b, and it is applicable for Reynolds number greater than 20,000 and less than 400,000, and Pesselt number greater than 0.2. The properties in this correlation is predicted at the film temperature, and it was deduced for air, water, and liquid sodium. This is the third correlation, and we may go to the other correlation which have been presented in the open literature as well. Here we have Morgan correlation in 1987. It has been also prepared in the form Nusselt number equal to constant times Reynolds to power m, Prandtl to power 1/3, as presented in equation number 4, and table 3 is used to um, estimate the values of C and M to be used in equation number 4, and it is applied up to Reynolds number 2 times 10 to power 5, and all the properties are calculated at the film temperature. We have also Tarad correlation in 2000, and it has been prepared in the same form as Morgan equation, and it has been deduced from experimental data up to Reynolds number 2 times t to power 10 to power 5, with C values and M values as obtained for air and its application. And it has been shown that this equation predicted the experimental data by a range within a range of plus minus 10%. Of course, it has been utilized for air conditioning purposes. Now let us take a practical case study for air stream that passes over an electrical resistance unit, which is called electrical heater, with a velocity of 40 meters per second, and the cylinder surface temperature was constant to be 150 Celsius, and we need to calculate the heat transfer coefficient, the heat loss per unit length, where we have the thermal properties as measured at film temperature of 90 degrees centigrade to be rho sub f, Cp, K, mu, and finally Prandtl number. Of course, these are in international SI units. Rho is the density, Cp heat capacity, K represents the thermal conductivity of air, and the mu is the dynamic viscosity, and finally Prandtl number. To start our calculation, we need first to estimate the Reynolds number, and with substituting the values of the density, velocity, and the outside diameter, as it has been specified in the figure, as 8 millimeter, then the Reynolds number will be 72,691.9, and Pesot number is calculated to be 51,843.9, which is already greater than 0.2. This is the conditions and limitations of our example. To estimate the heat transfer coefficient of air, I will use Hilbert correlation as presented in equation number 1 with Nusselt number C, Reynolds to power n, Prandtl to power 1/3. And from table 1, we may get C equal 0.0266 and M equal 0.805. Substitute these values in equation number 1. The Nusselt number will be 194.74. And from the definition of Nusselt number, we may get the air heat transfer coefficient to be 147.22 watt per meter square Kelvin. And this is the answer when we use Hilbert correlation. Another correlation, the rod correlation, as presented in equation number 5. Again, Nusselt number has the same form even as Hilbert and Morgan, as we have mentioned. And from table 4, we may get C equal 0.02 and M 0.82. Then Nusselt number will correspond to 173.2. Then the heat transfer coefficient of air from the definition of Nusselt number can be obtained to be 130.94 watt per meter square Kelvin, and this is the final answer for the estimation of heat transfer coefficient by Tarrant correlation. And finally, I will use Morgan correlation as shown in equation number 4 with table 3. Then C and M are obtained, which give heat transfer Nusselt number equals 168.42, and finally the heat transfer coefficient of air by Morgan correlation to be 127.33 watt per meter square Kelvin. To find the heat transfer rate per unit length, we have the general form of convection heat transfer Q equal H sub A times A, where A represents the surface area, times T wall minus T sub A. Then by Hilbert equation, Q dash equal to Q divided by L. And if we substitute the values of H, T wall, T sub A, and the diameter of the heater, then we will get Q dash equal 2220.03 watt per meter. Similarly, by Tarrant's correlation, we may get Q dash equal to 1974.53 watt per meter. And finally, by Morgan correlation, the heat transfer rate per unit length equal to 1920.1 watt per meter. As a summary for this example, we may find that Hilbert correlation predicted the highest value of heat transfer coefficient and heat transfer rate per unit length, whereas Morgan is the lowest. And Tarrant correlation predicted values lie between the higher and lower values as obtained by Hilbert and Morgan correlations respectively. We have even more correlations can be found in my published books entitled The Principles and the Practice of Heat Transfer, and I put it as a reference in the list of references in a link below this video. In the description box you may find it, and consult it to find more examples and correlations. And finally, my friends, we have arrived to the closure. We have passed through convection heat transfer concept and how it does work in industry. Then the methods uh, which are available to predict the heat transfer coefficient of fluid as it passes on external flow. And we gave some examples and references for such methods. And if you want to get more, please consult my book, which is presented in the list of references below this video. And we passed through a practical application where electrical heater resistance is used to heat up air in an air conditioning or industrial application. We have some valuable resources, as I mentioned. You may find them in a link below this video. And finally, if you feel that the information available in this video are useful to you and others, please uh, uh, subscribe to our channel, your channel in fact, and share this information with your friends. And thank you for your support, and see you in the near future with other aspects of the convection heat transfer coefficient and how can we predict it. Bye bye.